Good afternoon, students. Today we will start with the topic half-life period. Now we have already discussed about the various order reactions, and from there we have derived the integrated rate expression. So we have discussed about zero order reaction and first order reaction. Now we did not derive the integrated rate expression for a second order reaction because that is not directly there in our both syllabus. But when we will deal with half-life period, we will take the ultimate expression, and there we are going to see what is the expression for half-life period. Okay. Now what is half-life period? Now from the name itself we can make out what is half-life period. Period means an interval or the time taken. So half-life period is defined as the time taken to complete half of the reaction. Okay. So the time taken to complete half of the reaction, or we can say that it is the time period in which the original concentration of the reactant is reduced to 1/2. Okay, and it is denoted by T half, like this. Now let us suppose a general reaction like this, A to product. Now we have already discussed that suppose at time t equal to 0, that means initially if the concentration of the reactant is A, so the concentration of the product is 0. Now after a certain time t equal to t, let the concentration of the product be x. So what is the concentration of the remaining reactant? It is A minus x. Now if we consider a certain time which is t equal to t half, that means the half-life period, that means only half of the concentration of the reactant has been converted to product and half of it is remaining. So if the initial concentration is A, so half of it has been converted to product. So product concentration is also A by 2 and the remaining reactant is also A by 2. So 50% of the reaction is complete. That means it is the half-life period. Okay. Now what is the integrated rate expression which we have obtained for a zero order reaction? For a zero order reaction, the expression goes like this: K is equal to x by t. That was the expression for the rate constant. Now, so we can write here t is equal to x by k, right? Now here, when t becomes t half, that means it's the half-life period. So x becomes what? It is A by 2. So we can write like this. So here 2 is a constant, k is a constant. So t half we can say is directly proportional to A, right? So what we can deduce from here, that t half for a zero order reaction or for zero order kinetics, whatever we specify, is directly proportional to the initial concentration of reactant. Right? Now we are going to consider the integrated rate expression for a first order reaction. Now if we consider a first order reaction, so what was the expression? It was T is equal to 2.303 by K log A by A minus X. A represents initial concentration of the reactant and A minus X represents the remaining concentration of reactant after a time interval t. So when t becomes t half, so we can write it like this: 2.303 by K log A by a minus x. So a minus x is a by 2 because half of it is complete, so half of it is remaining. So from here what we can say, t half is equal to 2.303 by k log 2, right? So what's the value of log 2 base 10? It is 0.3010. So let us put the value here. Right? So what is the expression for t half? So we are getting t half is equal to approximately 0.693 by k. Now here if we look at the expression, 0.693 is a constant and k is the rate constant. So what we can say, there is no term a here. So here t half is independent of the initial reactant concentration. That is A, right? So what we have seen, for a zero order reaction it was directly proportional to the initial reactant concentration. For a first order reaction it is independent of the initial reactant concentration. Okay. Now let us consider a second order reaction. Now for this, if we have a look at the integrated rate expression, so there T is equal to 1 by K into X by A into A minus X. This is the form. Now here we are putting T is equal to T half. So again it is equal to 1 by K. So X means the concentration of product. So after the reaction is proceeded to half its initial value, so it becomes A by 2, and similarly it's A and A minus X is also A by 2. So this and this cancels. So what we are getting? T half is equal to 1 by K into A, right? So from here what we can say, that T half is proportional to 1 by A. Or what we can deduce, that T half is inversely proportional to the initial reactant concentration. A, right? Now if we now generalize this, we have seen the expression for T half for a zero order, for a first order, for a second order. Similarly we can check it for higher orders, third order, fourth order, like this. Okay, now so if we generalize this, so in general what is the expression for an nth order? Means it's not the actual expression, it shows how it is proportional to. Okay, so we can write in general, for a reaction of nth order, T half is proportional to 1 by A to the power n minus 1. So here n represents the order as it has been mentioned here, and A is the initial concentration, right? Now how to graphically represent this? Now what we are seeing, if we follow this expression, T half is proportional to 1 by A to the power n minus 1. So what we are getting? For zero order reaction, T half is equal to, since it is directly proportional to the initial concentration, so we can write T half is equal to K into A, right? Means if we consider that proportionality 1, So if you are going to plot the half-life period T half versus the initial reactant concentration, so it's directly proportional, and T half is proportional to a to the power 1. So what will be the nature? The nature will be a straight line, and it's an increasing plot. And what will be the value of the slope? Slope here is equal to k, right? Similarly, if we consider a first order reaction, for first order reaction, what we can write? T half is proportional to 1 by a to the power n minus 1. So T half is proportional to a to the power 0. So it's a constant. So what we can write? T half is equal to a constant k, right? So it is independent upon the initial concentration. So here if you are going to again plot T half versus the initial reactant concentration, what will be the nature of the plot? It will be a plot which will be parallel to the x-axis, because if you are going to change the initial concentration of the reactant, it's not going to alter the value of T half. Okay. Now, what happens for a second order reaction? So for second order reaction, what we have seen, T half will be proportional to 1 by a to the power 1, because it was T half proportional to 1 by a to the power n minus 1. So here we can write T half is equal to a constant by a, right? So here if we are going to plot T half versus initial reactant concentration, so what will be the nature? Rather 1 by a. So T half versus 1 by a will be an increasing plot having a straight line. Okay. So here also slope will be equal to k, right? So this is all about the half-life periods and their plots.